Hello viewers, today we are going to see Lecture 2, which is part 2 of Foundation Engineering 2, which is more concerned about deep foundation systems. Here are some concise introduction pointers for the presentation below, so that what we are focusing about is different methods and approaches in order to determine loads in pile capacity analysis. So basically, we are going to see different ways and approaches in order to determine the pile load carrying capacity. And also, we try to see the definition of those allowable load and how to calculate this allowable load with respect to factor of safety. And we try to see also the importance of factor of safety. And finally, what we are going to do is summarize the methods for the determination of this pile load carrying capacity. So that to start with, first, the most important thing is when we are thinking about piles is pile foundation length. So what does it mean by a pile length? So selecting the type of pile to be used and estimating its necessary lengths are challenging tasks. So this requires what? It requires sound judgment and through studies. In most cases, the required length of an end bearing pile can be established relatively easily. But the length of friction piles, however, depends on several factors. These include the shear strength of the soil, the applied load, and the size of the pile. So that to determine the necessary length of these piles, engineers need a solid understanding of the soil-pile interaction, and the process demands a good judgment and an experience. Here we can see three different figures. It shows that in figure A we have a top of a weak soil, and at the end we have a rock at the base, and then here in figure B, what we see is the top layer is weak soil, and the bottom layer of the soil is strong and firm type of soil. In figure C, here what we see is that the entire layer of the soil with total pile length is consisting of weak soil. So in these three types of piles, we are going to see in detail, in contrast, about how the load and the length is related. So understanding the soil condition is very essential to accurately determine the length estimation. So, for example, the end bearing pile lengths are generally easier to establish. As you can see, once you have the end bearing here at figure A, the rock, so that this is what we call the end bearing, so that the load, most of the load from the superstructure is carried by the end bearing, which means at the tip of our pile foundation. In contrast, for example, if you take here, we can have a combination of tip resistance and also frictional resistance. In figure C, we have frictional resistance only, since the entire soil layer is weak soil, so that the friction pile length depends on the soil shear strength, which is the shear strength parameters, for example, C and phi, and also the applied loads from the superstructure, and also the pile size and also shape. So engineers must have a strong grasp of soil-pile interaction, along with sound judgment and experience. Let's see the installation of a pile. Most piles installation is crucial for foundation support, so that most piles are driven into the ground using hammers or vibrator drivers. In special circumstances, piles can also be inserted by jetting or partial augering. Common types of hammers are listed below. For example, we can have a drop hammer, a single acting air or steam hammer. We can have also double acting and differential air or steam hammer, or we can have also a diesel hammer systems for driving a pile inside a soil. In the pile driving operation, a cap is attached to the top of the pile so that a cushion may be placed between the pile and the cap. So this cushion helps us reduce the impact force. Also, it also spreads the force over a longer duration. This technique enhances the effectiveness of this driving operation, so that we can have to install safely our piles. Here we can have a figurative explanation. The figure illustrates the details of pile installation. For example, as you can see in the figure, a cap is attached to the top of the pile, this cap, so that the cushion may be placed between the pile and the cap. Between the pile and the cap, we're going to have a cushion at this point, at the top of the pile. So this cushion helps reduce what? The impact force and spread it over a longer time, so that the hammer is used to drive the pile into the ground. This is the hammer from the top, as you can see in these two figures. So these figures show scenarios of pile driving. So this cushioning technique enhances the effectiveness of the pile driving process. This is more or less the same as the figure above. Now, let us see the most important critical thing in pile, which is the load transfer mechanism of a deep foundation or a pile foundation system. As you can see, here we have a figure that shows us the load transfer mechanism from pile to the soil, which is a complex process. As shown in the figure, the load transfer can be divided into different zones. As you can see here at the bottom of this figure, we're going to have like zone 1 and zone 2. In zone 1, for example, the pile tip bears the load and transfers it to the underlying soil. In zone 2, the pile shaft transfers the load to the surrounding soil through frictional resistance. So the frictional resistance is influenced by factors like the soil properties, shear strength parameters like C and phi, and additional parameters, unit weight, or other conditions, pile soil interference, and the applied load from the top. The overall load bearing capacity of a pile depends on the combined effects of end bearing and shaft friction. So understanding this load transfer mechanism is crucial for accurately designing and analyzing this pile foundation system. So this figure illustrates different components and zones involved in the complex pile soil interaction. Saying this, as you can see here from the previous figure in our slide, this illustrates how it is complex that the load transfer mechanism in a pile foundation system. For example, in case A, the pile is embedded in weak soil with rock at the base, so that most of the time Q ultimate here is equals to QP, so that we call this end bearing pile system. In case P, the soil profile consists of weak soil at the top, so that we can have a resistance due to QS, which is skin frictional resistance, and a combination which is the end bearing resistance, which is QP at the bottom of the soil, because we have what relatively strong soil layer below, so that the depth of the penetration into the bearing stratum, which is denoted by LB, is critical. So that this is crucial factor in determining the load transfer from the pile to the strong soil layer. In case C, as you can see, the whole layer is weak soil, so that in this scenario, the ultimate load capacity is mainly governed by what? The shaft frictional resistance, we call it QS. So understanding this diverse soil condition and their impact on the load transfer mechanism is essential for accurate pile foundation design. The third part, which is pile capacity. So the bearing capacity of pile can be determined using different approaches and methods. And as you can see here, we have 5 listed methods. From this, the most reliable method is conducted on a full-scale loading test on the piles. So building codes also provide guidelines and recommendations for estimating pile capacity. The another thing is, let me get back. So that from the lists, as you can see in the above slide, the most crucial and appropriate way of determining the load bearing capacity is by using loading test, which is the approach number 1. Determining the bearing capacity of piles is critical aspect of foundation design. One of the most reliable methods, obviously, to do the full-scale loading test. Here, as you can see, we have a load transfer method, which shows load settlement curves from pile loading test. So the graph illustrates a load settlement curve, which are crucial for determining the bearing capacity of piles. So these curves depict the relationship between the applied load and the resulting total settlement of the pile. So the vertical axis, as you can see, represents the total load, which is acting on the pile, while the horizontal axis shows us the total settlement or the displacement. And then the curves are, as you can see here, we have in the horizontal axis the loading, and here we have also what we call the settlement. So that the curves are labeled with various references, for example, including the industry standard building codes or the scientists that studies like Terzaghi and Peck, Visek, New York City building law, and others. These curves provide guidelines for just suggesting limiting loads, which are maximum loads that should be applied to the pile to prevent excessive settlement. So the shape and the position of the curves indicate the load bearing capacity and the settlement characteristics of the pile, which are influenced by factors like soil property, pile material, and installation method. So analyzing this load settlement curve helps engineers determine the optimal pile design and ensures the long-term performance and safety of the foundation system. So understanding and applying this industry-recognized load settlement criteria is essential for reliable capacity assessment and foundation design. So this is more or less the same. There are several methods to identify the limiting loads. For example, if you take the point where the end tangent of the curve intersects these points, which are in dark. The second is the point where the curve begins to show steeper slope. And the third is the point of the maximum slope, which represents the steepest part of the curve. So seeing and choosing these three methods to identify our limiting load, the limiting load can also be determined based on specific total settlement criteria. For example, 0.1 times of the pile diameter, or you can take a maximum settlement, which is 50 millimeter or 25 millimeter or 20 millimeter, based on what? The scientists, you can see that value on the y-axis. We intersect with the type of method. For example, if you take number 4, which is the Terzaghi and Peck method, it says 0.1 times of d. D means the diameter of our pile. ለምሳሌ, for example, Terzaghi and Peck, number 5, which states 50 millimeter. 50 millimeter is the limiting settlement. Alternatively, the load plastic settlement curves can be used, where the limiting load is based on the plastic settlement, which is 0.25 times of the pile diameter, or 0.02 times of the diameter, or 8 millimeter or 35 millimeter. These are what shows. This also provides the most reliable data for assessing the true capacity of pile, ensuring the safety and the performance of this pile foundation system. This curve comes after a lot of field practice and field studies and researches. So another way to determine is using the sounding test to determine the pile capacity. For example, from the sounding test, we can take cone penetration test or stand-up penetration test, which are relatively easy to perform cost-effective way of pile capacity. When carefully interpret these results from sounding text can offer reliable insights into the pile capacity. So we can see deeply these tests can give us our pile capacity by using a correlation formula. In the next slides or in the next lecture materials, we are going to see in detail the approach, how engineers assess the soil conditions and evaluate using this field study, field tests, so that incorporate that and find out the full-scale loading test and determine the pile capacity. Okay. The third is dynamic pile driving formulas. So this method is one way or another approach to assess pile capacity through the use of this dynamic pile formula. These formulas estimate the dynamic resistance to penetration of pile based on parameters measured during the pile driving process. The key advantage of dynamic formula is rapid application of loads, which makes them suitable for cohesionless soils where pore water pressure do not have time to develop. So the formula takes into account factors such as hammer energy, pile weight, and the distance of the pile is driven per blow to the calculate of ultimate bearing capacity. We can see some formulas from, for example, engineering news and others from the standards of those pile driving equipments, so that we can determine the pile capacity. So engineers must apply appropriate safety of factor when using dynamic pile driving formulas to ensure the long-term reliability and performance of the pile foundation. Most of the time, the factor of safety to be considered is 3 and above, so that we can have a safe value of pile capacity. Saying this, as you can see here, we have already discussed the ultimate dynamic resistance by a factor of safety 3 can be divided, so that we can say the Q allowable using pile driving formula. Pile driving formula can be the Q ultimate of the pile driving value divided by the factor of safety, which is equals to 3 is the value, a minimum value. Now, the last and method is determining the ultimate load carrying capacity of pile using analytical method based on the mechanics principle. This is more or less using equations, but the equation of this ultimate pile capacity is given by Q ultimate, which is equals to QP plus QS. QP stands for load bearing capacity of the pile point, or what we call end bearing resistance, whereas QS is for frictional resistance, skin frictional resistance between the pile and the soil. So this analytical approach allows engineers to calculate ultimate pile capacity by considering the specific soil condition and pile geometry. So the tip resistance, which is QP, this QP can be determined based on the soil property and the cross-section area of the pile tip, at the type of the pile tip. For example, we're going to have a square pile, or we're going to have circular pile. It can be steel, it can be concrete, it can be timber, whatsoever the case, but cross-sectional value of this pile is important for determination of the tip resistance, including the soil property. The second is the skin friction, which is QS, is calculated. For example, whenever we are discussing about QS, we are thinking about the pile and the soil interaction and the surface of the pile, which is the perimeter. Taking the perimeter multiplied by the length, it will give us the total area in contact with the soil of the pile. So that and the shear strength of the surrounding soil is very important for the skin frictional resistance determination. By combining these two components, the total ultimate capacity of the pile can be estimated through this analytical method. This approach provides a more theoretical basis for assessing pile capacity compared to empirical methods, but it still requires careful consideration of soil parameters and pile installation conditions, so that this analytical method of determining pile capacity is useful complement to other assessment techniques such as load testing and sounding test to arrive at a comprehensive and understanding of the pile load bearing capacity. So let's dive into the analytical determination of bearing capacity. In the analytical determination of bearing capacity, various methods have been proposed by researchers to calculate determine the point bearing capacity and the skin frictional resistance. So the point bearing capacity can be derived from general equations for calculating bearing capacity of shallow foundations, as we have learned in the previous course, which is Foundation Engineering 1. You can remember that the Terzaghi equation, which is QP CNC plus QNQ gamma D and gamma, so that I'm not going to dive in detail about this. You can see that these values are what we call the bearing capacity factors. Bearing capacity factors. Considering this, however, as you can see, pile is a very deep system created below a ground, so that D value, which we call it the width of the foundation, or what we call it, this D value, however, since the depth D is relatively small to the breadth B, which means this D represents the width, as you all know, so that we can simplify this equation by omitting the term without significant error, so that this will become 0, so that this D result, which is the cross-sectional width of this foundation, is relatively small. So, however, since the depth D is relatively small, so I've already discussed about it, the remaining equation will be QP, which is CNC plus QNK, which is the total point bearing capacity QP, then be calculated by taking area of the pile at the bottom multiplied by CNC plus QNQ. So as you can see, AP represents the area of the pile at the tip, So let's draw a 3D diagram. If it is a circular pile, what we are considering is as a tip is this area, the circular tip area, which is directly in contact with the soil at the bottom. This is what we call QP. So in order to determine the QP, we need AP, which is the area of that pile tip. C represents the cohesion of the soil supporting the pile tip, and QP, which means small QP, which means this one, represents unit point resistance. Q is effective vertical stress at the level of the pile tip, and NC and NQ are called the bearing capacity factors. So, in addition to point bearing capacity, the frictional resistance QS is also a crucial element that plays in determining overall load carrying capacity of the pile. So that, as you can see, the frictional resistance can be calculated using the equation, which is the summation of P, which is the perimeter of the pile section, and changing in length is represented if we have different layer of soils, we're gonna have different soil properties. That's why. And then F is unit frictional resistance at any depth Z. So this equation sums the contribution of this frictional resistance along the length of the pile. For example, let's say if you have a pile like this, and this pile have two different layers, so that the frictional resistance is resisted by the sides here. So this plays a key role. Let's say the top cross-sectional is circular, so that for this circular we can determine the area to determine the tip resistance. But to determine the frictional resistance, we need to determine the perimeter and multiply it by the total length. But we have different layer of soil. That's why in the formula we say change in L. We may have L1 and L2. two layers because we have different soil properties here. We can have here C1, we can have C2, we can have Phi1, we can have Phi2. So that these different soil properties can give us different unit frictional resistance between the soil and the pile. So the unit frictional resistance F also varies with depth and is influenced by the factor of the soil property or the soil type and the pile installation method. B, by using this accurately, calculating QS, engineers can be better assess the total load carrying capacity of the pile, ensuring the safety and effective foundation design. So that saying this all, the allowable load, the most important part. We have different types of load calculation. We can have Q ultimate, Q allowable, yes. So to determine the Q allowable, which is most important thing for our design, the equation will be Q allowable, which is equals to Q ultimate over the factor of safety. Most of the time, the factor of safety ranges from 2.5 up to 4 based on our design approach. This range depends on the uncertainty surrounding the calculation of the ultimate load. Let's say if you are having if your soil study, like the parameters used for the soil study, while estimation the C value, the shear strength parameters or other factors, if you have some errors, you may increase the factor of safety so that you lower the value of Q allowable, which means you assume that the load carrying capacity of that pile is lesser so that you can have a better design for that single pile. These ranges depends on the uncertainty or the soil type. For example, if you have a weak soil, you may increase the factor of safety so that you can have a good design for your pile foundation. A higher factor of safety may be applied in case of significant uncertainty, like variability in soil condition or weak soils. So for various methods are employed to determine the component of pile capacity, QP and QA, that we are going to see in the next tutorial classes or lecture classes. For example, we may use the Maroff method, we may use Castello method, we may use different approaches. Like in analytical way, we can use also a method which is called the SPT method, CPT methods. These all methods are going to be discussed in this next lecture materials. Understanding these methods is essential for accurately assessing the allowable load and ensuring the safety and performance of our pile foundation. So in summary, the determination of the Q allowable, here the main point, is a fundamental aspect of our pile design. So reflecting the need for careful consideration of safety of factor and soil behavior is very important. So I thank you for your attention. So in the next slides, we are going to see the analytical approach or the analytical method to evaluate our load bearing capacity. Here are some reference materials used for this preparation of the slide. Thank you.